Hello everyone, I am Zhiming Hu. I'm here to present our work called HOIMotion, forecasting human motion during human-object interactions using egocentric 3D object bounding boxes. The co-authors are Zhiming Yin, Daniel Hilfer, Xin Smith, and Andreas Bulin. We're from University of Stuttgart, Bionic Intelligence Tübingen Stuttgart, Heidelberg University, and University of Tübingen. Here is the outline of my presentation. I'm going to introduce the research background, related work, method, results, discussion, and conclusion. Well, human pose, it can usually be represented using the 3D positions of human body joints. Human motion forecasting refers to the problem of predicting human pose in the future from the pose in the past. Well, human motion forecasting can be applied to many XR applications, including human agent collaboration, redirected working in XR, low latency and precise interaction in XR, and safe and comfortable interaction in XR. Well, the motivation of our work is that we observe that while in daily human-object interaction activities, the human body movements are strongly influenced by the scene environment. For example, in this figure, the human is trying to pick up some objects on the table, and then his trajectory would be strongly influenced by the location of the table, and his detailed arm movements are influenced by the position of the specific objects. So we explore to use the scene object information to guide human motion forecasting. The main contributions of our work is that first we demonstrate the effectiveness of the egocentric 3D object bounding boxes for motion forecasting. We propose a novel GCM-based method to forecast human motions from body pose and egocentric object features. We conduct extensive experiments on two public datasets and report a user study to show the superiority of our method. Here we're going to introduce the related work. Human motion forecasting has been explored by many researchers in the area of computer vision and also robotics. People have used the recurrent neural network to do the motion forecasting by using the human pose in the past as input and then to forecast motion in the future. The multi-layer perceptions have also been applied to do the motion forecasting. And also the attention-based architecture have also been explored to do the motion forecasting. Well, recently, researchers have started to use a graph convolutional network by viewing the human body joints as a graph to do the motion forecasting. Well, traditional methods on human motion forecasting usually simply they predict the human pose in the future from the pose in the past. What we do is that we extract features from the scene objects, and then we predict future poses from the past pose and the scene object features. Well, here is the problem formulation of our work. We focus on the daily human-object interaction activities because in such kind of activities, the human motions are strongly influenced by the scene objects. We use the egocentric 3D object bounding boxes to do the motion forecasting because the object bounding boxes can be easily accessed in the XR environments. Our method is called HOIMotion, and it contains three main components, namely the post-object feature extraction, post-object fusion, and the motion forecasting. In the post-object feature extraction path, we extract features from the pose in the past, from the user's head orientations, and also from the dynamic and static objects. Well, the dynamic objects refer to the objects that the users can interact with, while the static objects are the background objects. We use a spatial temporal graph convolutional network to extract features from the body pose. We use the MLP to extract features from header rotations and the scene objects. All the information are transformed using a discrete cosine transform, namely the DCT transform. Well, to do the post-object fusion, we treat the scene objects and the body joints as nodes in a graph. And then by doing so, we build a fully connected spatial temporal graph. And such kind of graph can be processed using a spatial temporal GCM to do the motion forecasting. Well, in the motion forecasting part, we use a spatial temporal GCN, which consists of a temporal GCN and a spatial GCN to extract the features. We use a residual GCN block to extract the features, and then use a decoder GCN to map the features back to the body poses. Well, we evaluate our method on two public datasets, namely the ADT dataset and the mortgage dataset. Both datasets contains the full body motion and the scene objects in various daily activities. We use the mean per joint position error as our metric. We use 10 frames in the past as input and 30 frames in the future as output. Here are the results on the ADT and mortgage datasets. The best results are marked in bold, and the second best are underlined. We can see that our method can achieve best performance at different time intervals at different datasets. We also observe that our method using only body pose as input, it can also achieve better performance than prior methods. This validates the overall benefits of our model architecture. Here are some visualization results. We can say that at different time prediction times, our predictions are more close to the ground truth than other methods. We also conducted an application study to evaluate the effectiveness of each component used in our method. For example, we remove the static object, the dynamic object, static and dynamic, the head orientation, and we find that while our method outperforms the ablated versions at different time intervals, this validates that each component used in our method contributes to the overall performance. Well, here are some visualization results of the application study. We can say that our predictions is more close to the ground truth than the ablated versions. This video shows some of the visualization results. We can say, at different activities, our predictions is more close to the ground truth than the predictions of other methods. We first conducted a user study to evaluate our performance. We used 20 samples randomly selected from the results and recruited 20 users to do the study. The participants are asked to rank different methods according to precision and realism. Here are the results from the user study. We can see that our method outperforms other methods in terms of both precision and realism. Here we discuss some limitations of our method. First, we find that our long-term motion forecasting performances are not as good as its short-term performances. This is a well-known problem in motion forecasting because with the increasing time of the predictions, it will be much more difficult to do the prediction. And our method is designed for the human-object interactions, and it may not work well for human-human interactions. Well, here we give some avenues for future work. First, we would like to explore other scene object-related information, such as object shape for motion forecasting. And we will also like to add some physical constraints for the predicted human poses to make our predictions more physically plausible. And finally, we would like to integrate our method into more motion-related applications, such as redirected working and the human-agent collaboration. Well, to conclude, the main contributions of our work are, first of all, we validate the effectiveness of egocentric 3D object bounding boxes for human motion forecasting. Second, we propose a novel method that consists of 3 components: the post-object feature extraction, post-object fusion, and the motion forecasting. Finally, we demonstrate the superiority of our method through experiments on 2 public datasets and a user study. The code is available at this link. Thank you for your listening, and here are the references used in the slides. I'm looking forward to your questions. Thank you.